David Smith here with another Flipped Classroom math video. Today I will be explaining page 16 of the Orchard Hideout unit. This assignment is called a perpendicularity proof. Try to get that out. Okay, so what I'm going to do is share my screen here with the homework exemplar. Okay, great. Let's zoom in just a little bit, make that a little bit easier to see. Let's try right about there. Okay, so here's the diagram from the book. We have segment AB and it's bisected by line L. And so they're telling us that's our given in this proof. L is the perpendicular bisector of segment AB. So I went ahead and noted a few things on the diagram just to make sure that all that information is correctly displayed. These two little tick marks here indicate that segment AC is equal to segment CB. And that's what comes from it being a bisector of segment AB. So it cuts it into two equal parts. That's what that means. Additionally, line L is perpendicular to segment AB. So I marked that with a 90-degree angles there. So I have my givens, I have my diagram, and my givens are marked on my diagram. Now there's two ways to solve this one, two ways to prove it. Actually, there's probably quite a bit more, but I'm showing you two in this assignment here. Okay, so proof number one. I write my steps on this side and my reasons for the steps on that side. So I'm saying AC equals BC. That's what we talked about right here with these two tick marks. And that just comes from the definition of the perpendicular bisector. Now I'm going to tell you that angle ACD and angle BCD are 90 degrees. This also comes from our definition of a perpendicular bisector. So now I have a side, two sides that are equal, two angles that are equal, and now I'm going to tell you that CD equals DC. This is just saying this line segment here from CD is the same and it equals itself. That's the reflexive property, something equals itself. So now I have two triangles, ADC and BDC, and I can call them congruent. So that's what this notation is right down here. Triangle ACD is congruent to triangle BCD, and this is SAS congruence theorem. That's side angle side. And what that means is if you have two triangles and you have two sides that are equal in each triangle and the angle between those sides, or the included side, that's also equal, then you can say that those two triangles are congruent. And as a quick review, what that means is that the two triangles are essentially identical. You can flip and rotate one triangle and it will fit right over the other triangle. They're basically identical. Once you've said that two triangles are congruent, then corresponding parts of those two triangles are always equal. So all the angles that correspond are equal and all the sides that correspond are equal. So here that leads me to my last step, AD equals BD. These are corresponding parts of congruent figures. That's this theorem here, CP-CF theorem. And this proves that point D is equidistant from points A and B. So that's the first proof. There's another way to do that, and that's using substitution and the Pythagorean theorem. So let's scroll down to proof number two. This one takes a little bit more steps. So step one there, I wrote the two steps that we started the previous proof with. AC equals BC and angle ACD equals angle BCD, which is also 90. That's the same reason we listed above, definition of perpendicular bisector. Now we're going to talk about those two triangles, ACD and BCD, and we're going to say that they're right triangles because they have 90-degree angles. So let me scroll up, and here we go. This triangle, ACD, and triangle BCD are right triangles. That's what we talked about just down there. So scroll back down. Okay, so the Pythagorean theorem in right triangles says that the squares of the two legs, when added together, are equal to the square of the hypotenuse, which is the long side, the side opposite of the right angle. So I wrote two equations here, AC squared plus CD squared equals AD squared, that's for the first triangle, and BC squared plus CD squared equals BD squared for the second triangle. So these are just the setups for the Pythagorean theorem, and here's the reason I can do that. It is the Pythagorean theorem. Let's scroll back up. So what I'm saying here is AC squared plus CD squared equals AD squared. And the same for this little triangle down on the other side. Scroll back down. Okay, so now I can say AC squared equals BC squared. This is squaring both sides of step 1 above. Okay. And then finally on this step, I can say AC squared equals CD squared equals AD squared. And then this other equation here, AC squared plus CD squared equals BD squared. Notice here, what I'm doing is I'm substituting AC squared for BC squared. And that gives us two equations that have the same thing on each side, or on one side, AC squared plus CD squared and AC squared plus CD squared. So these two things are the same. That's going to lead us to be able to say this has to be equal to that as well. So I'm just simplifying that equation after I use substitution. And I get to AD equals BD. I've just simplified everything, and I've proven that the distance from D to the line is the same on both sides. So this proof is a little bit more complicated. If you like the video, give me a like below. Feel free to subscribe. Thanks for watching.